Hi everyone, it's Nono here one more week, and I want to welcome you to my live stream on creative coding and machine intelligence for designers. If you're new, I'm Nono Martinez Alonso, and we're going to do some coding today. We're going to continue with something called virtual sketching. Is a machine learning based sketch vectorization model that is open source, and I found online, and we've been using it for some live streams now. So this is a hands-on video where we're going to be taking a look at code, at some things that we did before, and we're going to get started right now. I have the chat here on the side, so I would appreciate if you're online that you let me know if you can hear me okay, if you can see me okay, and if everything's good. So without further ado, I'm going to get started. Okay, as always, a quick reminder, like the video if you want to support the work that I'm doing here with the live stream and the channel and the podcast and all that stuff, and subscribe if you want to get notified when I go live next or when I upload new videos. You can also join the community. This is a Discord server that you can join either at the short URL you can see here or at none of them as Discord or using that QR code up there. And yeah, so we've been covering this topic for some time now. We did a live stream back in live 39, and that was in September, but we went back to using this tool, I think 2 or 3 weeks ago. So you can go to live 62 and 63 if you want to see more of this. And I'm recording, as I think I mentioned last week, I'm recording soon an interview with Andrew Witt talking about his book Formulations, which talks about the intersection or like the evolution of mathematics and architecture, right? Like all the parts in history over the past centuries that those have come together. Also, there are things like biology, science, crystallography, stereoscopy, and many, many things, even getting up to today, like how computation and black box algorithms and other things are affecting the design practice and how we not only make architecture, but how design and we make art. So you can send the question to gettingsimple.com/ask. You can put it on the chat, on Discord, wherever, and we'll be happy to discuss it on the podcast if you send it before we record, which will be probably next week. Okay, so goals. We keep emphasizing this goal here of this second season of the live stream, which is building a collaborative AI sketching platform. And at the moment, we've left aside the application that we're building in React and using Perfect Freehand, an open source repo for free drawing on the web. And we're looking at a specific algorithm that maybe in the future we can use also for that. And I have to say, we have, I'm collaborating with some people trying to see how we can make this intro to machine intelligence for designers course advance a bit, because we haven't done a lot of work there. Okay, and yeah, so what are we gonna do today? I said something before, and we're not editing at the moment these videos, but maybe in the future we do. So I'm gonna record a quick intro here, and that way we could edit this as a playlist, right? Okay, so I'm gonna record an intro. We'll keep going. Hi everyone, it's Nono here, and this video is part of the Intelligence and Sketching playlist. Today, specifically, we're going to continue looking at an AI sketch vectorization framework called virtual sketching. And without further ado, I'm going to get started. This is a quick recap on what we've seen before. So this is what virtual sketching can do for you. If you input the faded drawing that is on the back, which is a line drawing, you're going to, in many cases, at least when it works, you're going to get these animations or like a vectorized version that you can export to SVG or render as raster images of your illustration. We've done this on past live streams. This is from live 39. And we have experiments here. This is from live 62, I think, or 61. in which we were trying to see or getting up to speed with the same Colab notebook, which we had to update. And what you can see here is a comparison between real raster input, that's a sketch scan that I've edited in Photoshop. And on the right, we have the same version vectorized by this algorithm, which means that we can scale up that vector graphic on the right as much as we want, and we can animate it as you saw before. These are, and I'm really proud that this worked. These are two examples that worked. The one on the left worked better than the one on the right because the one on the right isn't super complete. But you can see on the right is rewriting my handwriting with like this GIF animation, and on the left you can see an entire drawing of a ceramic worker that I did in Cordoba, in Andalusia. So this is what we're taking a look at, and what I realized last week is the code to generate these animations and to actually make sense of the output of the model is not trivial. It is actually running inside of a TensorFlow session. I hope it's not running inside of a TensorFlow 1 session, because that means that the code is going to be a bit old. But trying to do two things, right, on the next live streams. I'm trying to see if we can get the X and Y coordinates of each of the points of each of those strokes that you're seeing that are rendered on screen. And the second thing is trying to understand how the actual code, the code with that window, the red box, how it actually works. All right, so there is also an option to export to SVGs. So single SVG actually allows you to have each individual stroke as with a different thickness, that at least it gives a bit of sense of the original drawing. But the authors of the paper say that this is not the method that they used on the outputs that are shown on the paper, because those actually have strokes with variable width, right? So that means that you can have start really thin and end really thick. But here, if you zoom in close enough, you'll see that that sense of thickness transition is just that these are different strokes probably, right? You can see it pretty well here. And cluster means that we actually just have a group and everything has the same thickness. But what is cool is that, these are the same strokes drawn in two different ways, which we can do because this is vector. And a quick recap on the notebook. So we have this column notebook, which we have to update or add some code to make sure that it was running Python 3.6. And I'm remembering now, it does run in TensorFlow 1.15. This is why we had to run this on Python 3.6. And yeah, there's some other logic which we're not going to go through, which is clone the repo and do a few operations and zip the pre-trained model. And then we run this command to vectorize an input image that we can upload into the notebook if we're running in Colab. And our next steps, these are some slides that I just did really quickly at the end of the last live stream, because we were seeing there was this differentiable pasting graph, which I don't have any idea of what it is, and also a few methods, right? We have the method of or the class of div pasting v3, and some other concepts. Like here we have utilities, which is like image pasting v3 testing, and I'm not sure what these are. There is a concept of a patch canvas, a cursor, the image size, the window size, and that seems to be because the window that we see is drawing this vector is actually moving around the drawing. And this that you can see here, this says dot, this is actually a TensorFlow session object, and this is a TensorFlow 1.15 object. And that is a concept that you have to prepare the session and pass it some arguments, and then you would basically run it. Right here, we're passing like an image from the function, and we're passing like feeding it with a dictionary. So we'll have to see what all that is. So yeah, this is a bit daunting in terms of not sure if this is gonna happen all today live, but I'm here. I see there's some people online. So hello, Jose Luis, and hello Sajeh. I'm gonna get started, and feel free to drop any questions from this or off topic or some other things. And yeah, let me know how it goes. I was thinking that maybe at some point we could do some more workshop like sessions, and that would have to be in Zoom or some other platform where we can be connected real time and people can follow and ask questions in real time to follow the exercise. But for that, I'm meaning to prepare other type of content that is a bit more prepared. Right now this is a exploratory work, and I've been talking for 10 minutes, so let's get coding and let's get started. All right, let's close Keynote. I would say today I don't have too much time, so I have one more hour, I think, and I have to go. But yeah, we'll see. So let me do a bit of housekeeping here. Okay, we're back. And da da da. Cool. All right, so let's create a folder for Live 64 in here. And of course, it's empty. And we have these things from Live 63. These are the things that we generated. So this is the SVG, and this is one of the GIFs. So let's go to, let's open a new window here and let's try to understand. So virtual sketching, GitHub. So what I'm doing right now is I'm trying to understand a bit more the logic behind what is being done on this code, right? Pipeline at each time step. Right, so you can see this thing here. So we get an input. So this would be, this sig here would be our line drawing, and we have our canvas at a given time. So this VI seems to be our patch, or I don't know how they're calling this, if it's, this is a patch or is a canvas. So this is cropping, stroke generation, stroke parameters. So this thing here seems to be outputting something, and Bezier curve parameters. And then there is a way in which those are rendered. Window pasting. So that's probably that differential pasting that they're talking about here, because this depends on T. Okay. Right. So let's open, we've opened this before. We have the code here, we have the, we're opening the paper. I'm not sure if I downloaded this. I do remember having this paper open and highlighting things. So let me quickly look if I have it. Hmm. Well, I don't know where it is. Okay, so our approach is a general framework for line drawing generation given an arbitrary image as input. As illustrated in figure 2, the framework is based on a recurrent neural network based model which predicts the drawing's strokes step by step based from the input image. Dynamic window of a square that moves around while drawing the lines. These windows with size W, a cursor Q, is able to move and scale after each time step. There are two advantages of using a dynamic window. First, it allows us to model images directly at full resolution, the resolution of the input image, while avoiding training difficulty. Second, it enables our model to scale up to an arbitrary resolution even though the model is trained on low resolution images. There is banging. We have construction close by. Okay, yeah, sorry, I can't do anything with that. So if the noise is really bad, we'll have to stop or something, or I'll just have to mute myself. Okay, so I'm gonna mute myself while the banging goes. Okay, so if you are connected, so you just connected, I'm muting myself until the construction workers stop on the bottom floor. All right, so I'm highlighting here. So I think we took a look at this paper, but we haven't really dived so deep to understand the code. So stroke representation is using the similar representation to SketchRNN, which we saw a couple live streams back. And there are these concept of like stroke generation, so align cropping, stroke generation, differentiable rendering, differentiable pasting, which honestly are a bit beyond my understanding at this moment. And I don't know, this is something that we could take a look at. I want to understand, I would love to understand the convolutional neural network CNN encoder and the recurrent neural network decoder part. That seems to be what it's used during the training loop. And then there is this differentiable rendering and pasting, which is what actually ends up generating the SVGs and the GIFs and all the other information that we're seeing. So let's see what else we could take a look at here. See, right. Okay, so this is the diagram that we had before, and here's where the neural network architecture is. Architecture stroke generator. We have a convolutional encoder, so the raster image is basically encoded here, and we're gonna see what those encodings look like, and then we decode them back to FC, and I think AT are the Bezier curve parameters. And then from there, they pass into what you see on the right, which is rendering. So they have the stroke image, and then C is the canvas. So this is pasting on the canvas. Okay, so this on the top, S is differential rendering, and C is differential pasting. Hello, Ricardo. Nice. Thanks for saying hello, and I'm glad that you're connecting with us. Today, this got a bit out of hand. This is a bit too technical, I would say, and I'm probably going to be a bit slow in looking at these things. But it's okay. I mean, as much as we learn or progress during this live stream, it's good. What have you guys been working on this time? Like, I know some of you have connected during the last live streams, but others haven't. So what's up? Okay. So let me quickly take a 1 or 2 minute break, and we'll be back. Where do we have the break thing? Break slide on. All right, I'll be back really soon. All right, we're back. All right. Okay. I'm gonna close this. Close this. We can get back here. Soft arc max. Differentiable pen state binarizing. Relative moving and scaling. Stroke generator. Okay, what is this section? Stroke generation. The starting control point x0, y0 should always be exactly at the middle of the dynamic window. All right, quickly here. So Ricardo says that he's been studying some metrics like FID, KID, and IS in an attempt to cross-validate some of my model's performance, also learning R language for statistical analysis. Nice. Yeah, that sounds like a problem that, it's really important to be able to validate performance of the model and validate whether your data set is actually good for the task you're trying to do, and also the model architecture. Okay. Okay. Oops. At each time step, blah, blah, blah. Okay. All right. So we have here misaligned cropping, aligned cropping, differentiable pasting. The image represented in a dashed grid is cropped by a window in black solid lines. With a cursor and window size that are not aligned with pixels. Naive cropping operation with a quantized discrete window produces a misaligned patch in the light blue area. The pasting phase, this area is padded with pixels in white to form the paste frame. The line cropping works on a window that is not necessarily aligned with pixels. It relies on a roll align operation, which resamples the cropped patch into fixed size. Line cropping, differentiable pasting. Okay. Chamfer distance. Here are some metrics. Chamfer distance perceptual score. So this is talking about raster training overall loss function. All right. So this is a long paper, and I have to say, like, I need to do a bit more studying on my own, because otherwise I'm not gonna have time to cover a lot today. And the limitations, qualitative results. Here we can see other frameworks that try to do the same. So This is quantitative evaluation with chamfer distance on the rough sketch benchmark. Jan et al. This is all right. Okay, so let's try to see some of that with code. So we do have the repository here, and we do have here, for example, the recurrent sketch RNN definition. Vanilla LSTM cell uses ortho initializer and also recurrent dropout without memory loss. Okay, so where is the sketch RNN paper? So the thing with this one is that the input is also a vector. It's trying to learn a sequence of drawings or like paths, right? Vector paths. So the task here is a bit different. Okay. Okay, let's take a look. BGG utils tools. So here we have the visualization tools that we were looking at last week. Utils, load checkpoint, create summary, save model, normal, depth draw. So we're drawing here draw strokes. Uh, okay, so let's see where this, I mean, at least what we can do today, let's try to look for where this draw strokes function is used. Test vectorization. Draw strokes. Strokes draw out. All right. Haha, outlog. Okay, so let's actually get back to our notebook. So we're gonna get back to, I want to print this out and see, because this seems like it's printing the parameters of our Bezier curves. So I go to my Colab, research.google.com. Okay, so I'm gonna close Sketch and Paper. I'm gonna open the notebook for Live 63. We're gonna continue working upon it, and we're gonna save a copy in Drive. Let's see. So this notebook is meant to work as is, but we're gonna do some editing. So today is 10th of March, and this is Live 64. As always, let me make this public to share to anyone with the link, so you guys can access it. And I'm gonna post that to the chat. So Colab notebook. All right, and let me know if you can access, if you give it a try. So I'm gonna put GPU runtime. We're gonna connect to it, and I guess the thing that we want to do, because we're gonna change the code, I'm gonna make a fork, and we'll clone my fork instead of this one, this original repo. Okay, so I already have a clone, and it seems to be up to date. So let's clone it. Let's go to Git. Let's do git clone this. We're gonna go to the desktop first, and we're gonna enter that folder, and I'm gonna create a different branch to make sure that we're not changing the original. So we enter virtual sketching, we create a new branch that's gonna be called Live 64, or maybe just Live, and we push this branch. So this doesn't list any branches now, but now we do have the Live branch. All right, so we're on the Live branch here, and inside of the test vectorization thing, we have a comment with a print. So there are a lot of print statements here, and drawn pixel, blah, 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 selected path, round. There are many outputs here, and important. Okay, this is what I'm interested in. So 398. So we're gonna edit this directory with Visual Studio Code. And what's happening? All right. Okay, cool. Let's see. I'll also take a chance to say hello to anyone who's online. If you want to say hi on the chat, I'll be happy to hear from you, and maybe you can let us know where you're connecting from and how you found us. All right. I do have this here, so we're going to go to test vectorization. So I've just cloned the repo here, and this is especially slow today. I'm not sure why. Visual Studio Code is doing this. Okay, so we go to line 398. That's what we said. And we're just gonna uncomment this and this. All right. So if you want to do it with the Visual Studio Code interface, let me just close a few things here. We could. I see there is some noise now, so I'm gonna use the interface and I'm gonna mute myself for a bit. Okay, so I press Control Shift G here and I get this source control panel on Visual Studio Code. So I click here on text vectorization, which tells me which lines were edited. Basically, it's like I removed this line and I added this ones, but really you just removed this red bit here. And I'm gonna go to the top panel. I'm gonna press here on state changes. This is like doing git add and test vectorization.py. And this is a git commit -m, and then the message I'm gonna type here, and comment vectorization prints debug printing. I press command enter, so that gets committed, and I can click on publish branch to commit push to live, right? So now when we go back to our repository, we're gonna get this notice that live had recent pushes less than a minute ago. So we can click there. We can actually see our change here on GitHub, and we can see that that code has been updated, right? So 398, this is now uncommented, and this as well. So we just need to go to the repository, change this for my name, say that the branch is live, and we should be good to go. So I'm gonna save, and I'm just gonna run all. And I see on the chat that we have Mohammed El Mesawi from Egypt. Hi, Mohammed. I think I've seen you at least on Jose Luis's live stream or on the Discord server. I don't remember, maybe both places, but yeah. You want to tell us something about what you're looking for to learn from this live stream, or what you think that I might be able to help? Okay, and this is executing now, so we do have this step here which has to install TensorFlow for Python 3.6, which is a bit slow and a bit annoying. And then we're gonna clone this branch. We're gonna do everything else as we were doing last week, with the exception that this image probably doesn't exist there. So maybe we could, while this is being downloaded, we could upload it there. I'm not too sure, but if this fails, we'll just update that part. And we'll have to mount the Colab disk. All right, so this is installing now. So we'll wait for a bit to see if this works. All right, so this keeps doing its thing. Any other comments from the chat? Any other things, or maybe questions? And I'm muting myself because there is, as I said before, some construction work, and I'm just silencing that. All right, so I'm muted and I'm still talking, so you don't hear me. And I'm gonna keep muted for a second, and I'll talk. Okay, so I'm gonna put this. I'm gonna put this image on the Google Colab. So that's gonna go in the clean line drawings folder. I'm gonna close this one. Just gonna put it here. And the reminder is that all your files will get deleted from Colab when the session is wiped. And we can put the name here, and we can predict. So just a reminder, this is, we're just running the algorithm as it is. We just made the notebook work, but there's nothing that we've changed here. And we'll think of changing other things in the future, but I need to understand the algorithm a bit better. And what we're expecting to see, so we look at processing, right? We're getting this print, so we're at line 344 now. And this, okay, so this is what we were not seeing before. So we have, nice, all right. Okay, so now we're understanding something more, right? So this is what I wanted to see. We have the flag, like the raw, soft, X1, Y1. I don't know what these are, but these definitely doesn't match. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so these matches. Raw, soft, X1, Y1, blah, 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 R2, S2. R2 and S2, I'm not sure what they are. Okay, so when we export this to, this is still thinking. All right, so we do get this, but these parameters then need to be rendered with the differential renderer, and I don't fully know what that process looks like, but it takes some time as well. Average stroke number 552, right? So during this compute time, I think the all of these strokes are tested, so it's not ensured that all of them are going to be rendered. They're rendered and they're tested to see if they match the image or not, I think. But don't I'm not sure completely. I'm just saying, like, this is what I think I just understood from the paper. And this flag here is, so we're zooming to here a bit more. If you go to the top, all right, so here we have the flag, and this flag means 1 and 0. I guess from what I see is like 1 is when we move the pen up, maybe. So these would go from 0 to 1 without drawing, I think. So this is a start of a new stroke, and these are points on that stroke, right? So we see some strokes are longer than others. All right, let's take a look at our output data. So the output drawing that we've generated, it seems like this one worked. So we got the prediction here. This is the prediction. How is this a prediction? Looks like the original. Again, let's look at the original. All right, so we actually have some code below which we're gonna see if it works. So we inspect this data, and so here we do have that the strokes data, so 78,94462. 78, where is that one? 78, no. 78, 9. 76, 79. Let's see if the first, not the same. This has 7, 78, 9. Okay, so let me just copy this quickly. So the first row, let's just put it here quickly. Okay, so this first row seems like it matches these numbers. Minus 1204. Okay, so it's the strokes data is this data without the raw and soft, which I don't know what they are yet. But let's see, strokes data, raw, straight, raw out, smooth. Don't know what that is. Okay, so after we've run that cell here, we can generate a GIF and SVGs. I keep looking at OBS because I muted myself before and I forgot. And I don't know if I'm, maybe I'm muted and nobody's telling me. All right. And yeah, let's see. Now I see there's some people, I would say, just a quick reminder to like the video if you want to support the work that I'm doing with the tutorials and the live stream, and subscribe if you want to get notified when I go live next or when I upload new videos. Quick plug. It helps. Okay, so this is generating the GIF, and that should be output somewhere here. Dynamic. All right, so we're gonna get the GIF here. Well, this is not the GIF, this is the comparison of the order it's drawn. And it seems like it is, but for some reason it got like a lot of noise. Like this one, it got to draw it with a lot of noise, probably because of the change in line thickness. I'm not too sure. And thanks for that like, whoever it was. I know that, you know. All right, so let's. I would say if I download the GIF right now, it probably is not. Okay, now it's complete, so I'm gonna download it again. And it's here. Yeah, you see there's like duplicate strokes, but this is impressive. Yeah, it's like adding a lot of them. And probably what happens, now that I'm understanding a bit from the paper, what happens is the the strokes, the secondary strokes that the network is drawing on top of the existing strokes are probably making the output look more similar to the original than without those strokes. And that's something that maybe we could, I don't know, once we have the strokes, how do we decide that we don't want to sketch those, right? That would be, but maybe it's that we need to clean up the input before, make a like a blurring and blurring the sketch and adding some, I don't know. This is really cool. One thing that I wanted to see is like if I can make these GIFs faster. So let's take a look at the code as well. Let's download the SVGs. So these are, and another thing I want to automate. I want to automate the renaming of these files. That this is probably something super fast. Let's do that. I want to rename. So because we have a variable here that is the MPZ path, and let's print that down here. So print MPZ path. Yeah, probably we don't need that. This is Python. And we have the output sampling seek data, right? So we're getting this seek data, and this is the MPZ, right? So we could actually get the name of this folder by removing the MPZ. So that's easy. So I'm going to go here and simply say replace MPZ with nothing. So this is my output there. And we can construct the path of the so this is dynamic. So this is GIF, SVG single, and SVG cluster path. Path and GIF. And yeah, these are all paths. OS path join, and we'll do output there. And then the name here is dynamic.gif. And we need to import OS. Let's make that a bit bigger so you see it. And so this is the name, the source name, and I'm going to import shutil here, shutil, because I'm going to do shutil move from this GIF path into the GIF path, but we're going to replace dynamic for so I do have a variable with the name up top, MPZ name. So we have to replace this with nothing on the MPZ name. Replace. Okay, so this now, so we do have this, and so let's forget about the SVGs for now. So what we want to do is we have these things, we have the GIF path, and we're going to move the GIF path or rename it to just the MPZ, so the file name. All right, as soon as so we'll do if, well, let's make it fail. So if we run this, this is gonna work. So this worked here. So now this is renamed to it has the right name. So if I download these, you can see this file has the proper naming, which is what I wanted. Yes, and if we do it again, it will fail, I guess, right? Because that file doesn't exist. So we'll do here if os path exists, GIF path, then we'll do that. And now it doesn't fail. And now we need to do the same with the other two files, which is gonna, we're gonna repeat code. So we just have, we can say, okay, rename file, and we'll do path. So the path file path from and to, and we're gonna do, just put this here. So path, we already have the path. So we'll remove this. So this is a GIF path still. And we'll just do, if the path exists, we're gonna move the path and we'll replace from to. So dynamic with file name, and we'll do the same with, because we need the SVG single path and SVG cluster path. So we'll do os path join, and the name of these files here is cluster.svg and single.svg. Cluster.svg and single.svg. All right, and here we'll change cluster for file name and single for file name. But here we actually want to make it so it does have the cluster thing. And the single. All right. So let's try that out. We could actually have changed it from within the script. So the script actually changes the so the script actually changes the way these files are saved. But you know, for now, I'll just keep it as what it is. All right, so these work now. We can download these files and we have them here. So I have cluster and single, and this is cluster and this is single. Single actually has different thicknesses, as I mentioned before. Right, so let's move this to Live 64's folder, which is for today. Yeah, this could have better names. I think they do have better names. Just that I saved them by drag and dropping, so we could save all of this. And we should automate also like the saving of all of these files. Okay, here we can see the, the sort of problem that we have, that many strokes are drawn on top of each other. But anyhow, this is not something relevant right now. We'll try to make that better in the future. Okay, so now we need to figure out what these things are. So we have the strokes row out. Where is this coming from? So let's take a look here. Strokes row out. Best result IDX. Strokes row out. Let's take a look here. Strokes row out. Okay, so this is what we were printing before. So this is what our function gets, our drawing stroke drawing function. Save sec data and draw strokes. Save sec data. Let me look for that function. Let's see if we can. Strokes data. States row out. So there are two different things. One is strokes row out and states row out. Oh, no. States. Index out values. Let me see. Oh, raw soft. State row out. Oh, okay. So this is a soft argmax or what? Stays soft, because this actually here is if you look at these numbers, so if you look at this soft, this is like almost 0 or almost 1, right? So the ones up here. Okay, so that's the index flag. All right, how is the flag obtained? Strokes row out. We get the first values as an integer. Flag list. Okay, so we're getting the drawing length, so the amount of strokes, by adding all the ones, which is the start of each of the strokes, and removing it to the amount drawing length. Okay. Well, we can say so in here in strokes row out, we actually do have okay. So this means that the NF MPZ, when we save the sequential data, we do have the um, the strokes data as the strokes data object is our raw strokes raw out. So basically, except for these two numbers, because we have the flag, we have everything else, and we have all of that in here. So with this data, we can load that, and that's how the algorithm does it. We could load that, and we could reconstruct everything. But what does this mean, right? Like, what do all of this mean? I guess we could try drawing all of those. That's the kind of the next steps, and let's define that here. Let's say get an MPC file. Read, what is this? Strokes data. Draw strokes. This is flag x y, so x0 y0. Okay, so this means that um, if we were to get, let's take a look at what this is. So maybe we can see that from the paper. So what the okay here. Following the parameter design in Huang et al., we define the stroke parameters Qt. So this is important for a quadratic Bezier curve. At each time step, the virtual pen along with the dynamic window moves to the ending position of the predicted stroke. If it's not necessary for a stroke to be done, sliding to a different part of the image, the model can choose not to draw the stroke by setting the pen state to pt equals 0. We call this movement only. Furthermore, the model can choose to change the size of the dynamic window at each time step by setting ST, which allows enlarging or shrinking the window size given the cursor movement. So the pen state to 0, not to draw the stroke. So let me see. Yeah, so this is what we were reading before. So here, where it says soft argmax pushes the pen state from the domain from 0 to 1, so it can be 0,005 or 0.99, closer to 0 or 1 when applied to a vector that has an index values 0 and 1 only. Soft argmax. Let me see if I can do that. Maybe we can do that here. So TF version port TensorFlow as TF. All right, so we're executing this in Python 3.6 probably. And just to test this, can we do TF math argmax? Can we do so? Okay, so that might be a different function. Okay, so let's continue looking here. Stroke generator. All right, so I have to go now, so we're gonna leave it here. Not a huge amount of progress today, but we've taken a look at a few things. You have the notebook there with everything that we've done, and I will see you hopefully next week. Let me see, what am I doing? All right, and yeah, I'd love to I'd love to hear your questions. If you have any comments for or questions for the podcast that I'm recording next week, if you have any comments or questions about what we're doing here over the past live streams, and I do need some time to try to understand all of this a bit better and hopefully prepare an explanation, because this is deep learning and there is a lot of stuff involved, and it's not easy to just go through these concepts really quickly. But I learned something today about this paper, so that's pretty cool. And it seems like there's a lineage with like a lot of former work from the similar papers from the same authors, and that's something that we could take a look at as well. So without more waiting, so we're gonna wrap up here. As I said, let me quickly go. All right, and I would ask you, if you haven't done so yet, to like this video if you want to support the work that I'm doing here, and subscribe if you're enjoying and want to see more. You can join the Discord community at None of the Masas Discord. And yeah, thanks a lot for watching, and I'll see you next week. Leave me a comment if you're watching this offline or if you're live now. Let me know if you're enjoying, and also what you would like to see next, or what things you've learned that you didn't know. That will make me really happy. Much love. I'll see you next week. Thank you.